Welcome to Visual Civil. Today we are diving into one of the most significant updates in Indian structural engineering, the release of IS 1893-2025. If you have been working with IS 1893-2016, get ready because the way seismic forces are defined and applied has changed dramatically. These updates are set to reshape how earthquake-resistant structures are designed in India. In this video, we will break down the key differences, explain what they mean for the civil engineers, and show how the new code brings India closer than ever to global seismic design standards. Let us begin with the first major change, the title of the standard itself. In earlier edition, up to the 6th revision of 2016, the code was titled as Criteria for Earthquake Resistant Design of a Structure. In Part 1, it covered general provisions along with clause specific to buildings. However, in the 7th revision of 2025, the title has been significantly expanded to Design, Earthquake Hazard and Criteria for Earthquake Resistant Design of the Structure Code of Practice. This change is not just cosmetic, it reflects a shift in philosophy. In IS 1893-2025, Part 1 now includes only general provisions. All buildings related design requirements have been separated into a dedicated Part 5. This restructuring brings greater clarity, improves usability, and aligns the code with modern system-specific design practices. Next major change is updation of seismic hazard map. The seismic zone map of India, defined under the IS 1893 code, has evolved over the years as our understanding of earthquake and tectonic activities has improved. The first official seismic zoning map was introduced in IS 1893-1962. At that time, India was divided into 7 seismic zones, ranging from Zone 0 to Zone 6. In 1966, the map was revised using newly available earthquake data and several zones boundary were modified to better reflect seismic risk. Between 1966 and 1984, India experienced a significant number of earthquakes. As a result, the seismic zoning system was simplified and reduced to 5 zones, from Zone 1 to Zone 5, with Zone 0 being eliminated. In 2002, the map underwent another major revision. The number of seismic zones was further reduced to 4, ranging from Zone 2 to Zone 5. This update adopted a major cautious approach, ensuring that even regions with lower seismic risk were designed with basic earthquake resistance in mind. In the 2016 revision, the seismic zone map remained unchanged, confirming the continued relevance of the 2002 zoning. In IS 1893-2025, a new Zone 6 is introduced to represent areas with extreme seismic vulnerability. This update marks the first major change to India's seismic zone map in over 2 decades, highlighting the growing recognition of elevated tectonic risk across the country. Up until 2016, the seismic zone map was primarily based on earthquake intensity and the location of past epicenters. However, in the 2025 revision, the approach has shifted. The updated map is now developed using probabilistic earthquake hazard assessment, a more advanced and scientific method that evaluates the likelihood of future earthquakes rather than relying only on the past events. With the introduction of Zone 6, the seismic risk distribution across India has been clearly redefined. Approximately 21% of the country now falls under Zone 6 that may experience very strong to extreme earthquake shaking, while Zone 5 covers about 7% of India vulnerable to severe ground shaking. Moving further down the scale, Zone 3 accounts for nearly 26% of the landmass where moderate ground shaking is expected. Finally, Zone 2 includes the remaining 37% of the country likely to experience low seismic shaking. This revised classification provides a clearer picture of seismic risk and underscores the importance of designing structure based on the actual hazard level, not assumptions. In IS 1893-2025, the site classification system has been significantly expanded and refined compared to the 2016 edition. Earlier, in IS 1893-2016, classified sites into just three categories: rock, medium soil, and soft soil. While this was simple, it often failed to capture the actual behavior of the different ground condition. Therefore, the 2025 revision introduces five site classes: A. Hard rock, B. Rock, C. Stiff soil, D. Soft soil, and E. Very soft soil. These categories are now clearly defined using engineering parameters such as shear wave velocity, SPT values, and undrained shear strength, removing ambiguity in site identification. As a result, seismic design becomes far more site specific, and the risk of underestimating soil amplification effect, especially on soft and very soft soil, is significantly reduced. In the 2025 revision, the design response spectra have also been significantly updated for both the equivalent static method and response spectrum method. One of the most important changes is that the design spectra are now extended up to a natural time period of 10 seconds. This update allows engineers to properly account for super tall buildings, long span bridges, and other structures that are sensitive to long period ground motions. In line with the updated design response spectrum, the normalized pseudo spectral acceleration corresponding to natural time period have been also revised for both the equivalent static method and response spectrum method. The new spectra now provide clearer and more realistic representation of seismic demand for different soil type, capturing variation in ground amplification more accurately than before. As a result, the seismic forces obtained from this analysis, especially for flexible structures and soft soil conditions, may differ noticeably from the earlier edition. In the 2016 revision of IS 1893, the seismic zone factor was fixed for each zone. The same value applied to all the building regardless of their importance or function. But in 2025, this approach has completely changed. Now, zone factor values are defined based on return periods, which means the seismic design forces depends on how important the structure is and what performance level is expected. Clause 5.5 of IS 1893-2025 introduces this new concept by classifying building according to return periods as shown in Table 1. Buildings are now divided into four categories. First, normal buildings designed for a return period of 475 years. Second, important buildings with a return period of 975 years. Third, critical building designed for 2475 years. And finally, special buildings with a very high return period of 4975 years. Now, based on this classification, Table 3 specifies different zone factors ranges from each category. For normal building, the zone factor ranges from 0.075 to 0.5. For important building, it increases to 0.1 to 0.6. For a critical building, it further rises to 0.15 to 0.75. And for special buildings, the zone factor can go as high as 0.94 starting from 0.2. In simple terms, the more important the building, the higher the return period and the higher the seismic design forces. This shift makes IS 1893-2025 more risk-based, performance-oriented and aligned with modern seismic design philosophy. Now let us move to another update, the modification of the importance factor. In 2016, the importance factor for building was primarily based on occupancy. Most residential and commercial buildings were assigned a value of 1, while important and lifeline structures were assigned higher values, typically 1.5. In 2025, introduces a fundamental shift in approach. Buildings are now clearly classified as normal, important, critical, and special structures. The importance factor I is taken as 1 for all 4 categories of the building, as the importance of the building is already embedded in the seismic hazard definition, specifically through the zone factor assigned to each building category. In essence, 2025 revision shifts importance from a force multiplier to a hazard-based parameter. In 2016, the design base shear VB was calculated using a relatively simple horizontal seismic coefficient method. This approach combined the zone factor, importance factor, response reduction factor, and the design spectral acceleration based on the structure's fundamental time period. In contrast, 2025 revision retains the same basic concept of base shear but significantly refines its application. The updated code introduces revised response spectra, stricter soil amplification effects, and mandates dynamic analysis for a wider range of structures. Most importantly, the 2025 revision explicitly introduces vertical seismic force computation. As a result, 2025 revision transforms seismic design from a simplified force-based approach to a more comprehensive, realistic, and structure-specific framework by fully integrating both horizontal and vertical seismic action. Now, let us move to one of the most significant upgrades in 2025, the provisions for dynamic analysis. When we talk about dynamic analysis, we typically use two methods, the response spectrum method and the response history method. The response history method requires actual ground motion records, and this is where the 2025 code makes a major leap forward. For Zone 2 and Zone 6, the code now provides far fault ground motion records in the respective table. In other words, engineers now have zone-specific three-dimensional ground motion data readily available for the analysis. The near-fault ground motions are provided only for Zone 5 and Zone 6. Overall, IS 1893-2025 significantly strengthened the response history method by providing comprehensive ground motion suits for all zones and specialized near-fault motion for the highest seismic risk regions. Now, let us come to another major shift in IS 1893-2025, the modeling of soil flexibility. In earlier edition, soil structure interaction was largely ignored. Most structures were analyzed assuming a fixed base or rigid foundation. That assumption is no longer acceptable. In IS 1893-2025, soil flexibility must be considered for important, critical, and special structures in all earthquake zones. This requirement applies to structures resting on site class C and site class D soil, where soil flexibility significantly influences seismic response. In addition, soil flexibility must also be considered for any structure in which effects of geometric nonlinearity enhances the stress resultant by more than 15%. So, what does considering soil flexibility actually means? It means the foundation is no longer modeled as a fixed. Instead, the structure is modeled as resting on the springs with vertical and horizontal stiffness values defined using the modulus of subgrade reaction. This approach applies to isolated footings, pile foundation, and well foundation. Now let us move to method of liquefaction potential assessment. In 2016, liquefaction was acknowledged but not clearly defined, leading to an inconsistent assessment. The new code introduces a simplified and well-established approach based on the factor of safety against liquefaction. The factor of safety is defined as the ratio of cyclic resistance ratio CRR to cyclic stress ratio CSR. The seismic demand or CSR is linked directly to design ground acceleration, while CRR represents soil resistance reference to a magnitude 7.5 earthquake and adjusted using a magnitude scaling factor. This update transforms liquefaction checks from judgment-based to code-driven, bringing Indian practice in line with the global seismic design standard. The 2025 revision introduces a new clause for architectural elements and utilities, commonly referred to as AEUs. In many earthquakes, buildings don't collapse but non-structural items fail. Items such as electrical equipment, architectural finishes, furniture, air conditioning units, televisions, refrigerators, wall mounting elements, and many other can slide, topple, or fall, causing serious injuries. More importantly, the failure of these elements can disrupt the functioning of the building. This is especially critical for hospitals and emergency facilities, which must remain functional immediately after an earthquake. Recognizing this risk, 2025 revision explicitly addresses non-structural seismic safety. The code classifies architectural element and utilities into three categories. First, acceleration sensitive AUs. Second, deformation sensitive AUs. And third, combined acceleration and deformation sensitive AUs. Each category requires specific protection measures to prevent damage and ensure continuity of the use. This update makes a major step forward, shifting seismic design from just preventing collapse to ensuring true post-earthquake resilience. That's a wrap on this video. If you found this video helpful, give us thumbs up and don't forget to subscribe for more design insights. Drop your queries or experiences in the comments below and we might feature them in our next video. Until then, keep learning.